Okay, so this is for the AQA A-level physics specification. This is on chapter 1, particles and radiation. We're going to go through a bunch of practice questions from the Oxford textbook, and these questions have all been taken from past AQA papers from the Legacy series. Okay, so let's get straight into it. Question 1 is asking us to look at the table and complete the table below. So we've been given a set of four different particles, and we have to deduce whether they're a particle or antiparticle, then state their relevant charge. So what we can say about that is, for the first one, the clue is really in the name. It is an antiproton, and if it's an antiproton, we know it's an antiparticle. The charge on the element over here, so because it's anti, we know it's going to be the opposite of a proton. Proton is +1, anti, therefore it's going to be -1 charge. The neutrino is a particle, it's not an antiparticle. If it were to be an antiparticle, we'd be talking about the neutrino, the antineutrino, and the charge on the neutrino is going to be 0, because we know that neutrinos are massless and chargeless. They have no mass or no charge. The neutron itself is a particle, it's not an antiparticle, and the charge given is 0. And as for a positron is to do with an electron. It's the antiparticle of an electron, so we know that there's an antiparticle. The electron has a -1 charge, and therefore the positron, clue's really in the name, positive, so it's +1 charge. Okay, that's how we do part A. Part B says that the tracks of a positron and electron created by pair production in a magnetic field curve in opposite directions as shown above. So that's referring to this diagram here. Why do they curve in opposite directions? So the reason due to that is because of the charges that they carry. We know that when we have pair production, we have a photon. So we have over here, if I draw it on the diagram, we have a high energy photon which comes in and it releases two particles. One particle going to be our electron and the other one will be our positron. Okay, so those particles will go in opposite directions, and that is essentially the basis of pair production. The reason why they go in opposite directions, as the question asks, is because they carry opposite charges. Okay, next question says both particles spiral inwards. What can you deduce from this observation about their kinetic energy? Well, if they're going inwards in a path, the spiral that they're going to take is going to look something like this. They're going to get slower as they get to the middle, and therefore their kinetic energy will decrease. So that's how we do the math. Okay, moving further down. Question number 2 says that thorium-229 is a neutral atom of thorium. How many protons, neutrons, and electrons does it contain? So what we can say from that is, if we're looking at the number of protons, it's given to us there by the atomic number as 90. Okay, and the number of electrons, because it's a neutral atom, the number of electrons over here is also going to be 90. And we can also say that the number of neutrons, we can calculate that by doing 229 take away 90. That gives us 139 neutrons. Okay, so that's the answer for that question. Part B says that thorium YX is a neutral atom of a different isotope of thorium, which contains Z electrons and give possible values for X, Y, and Z. Okay, right, so for that, it's a very open-ended question. You can pick anything that you want from those. So if I go from what we need to first of all know, though, is that the definition of an isotope, same number of protons, a different number of neutrons. Okay, so if we have element containing the number of protons has to stay the same at 90 for thorium. But we can change around the number of electrons, the number of neutrons, though. And so what we can say is that it has a Y value of, let's pick something like 2, 4, 6, and then the number of, that's Y is representing the number of neutrons, by the way, so I'll put neutrons there, and the number of electrons will also stay the same as the number of protons, being 90. Okay, so that's just an imbalance in the number of neutrons, corresponds to different mass numbers because it is an isotope. Okay, let's move on. So, question number 3. An atom of argon 3718 is ionized by the removal of 2 orbiting electrons. How many protons and neutrons are there in the atom? Okay, so again, fairly easy question. Because we have 18 up here for our proton charge, it's going to have 18 protons. 37 take 18 gives us 19 neutrons. So that's the answer to part A. Part B, what is the charge on the ion? So the charge on the ion, because it is has the removal of 2 electrons. If you think about it, first of all, ions are neutral overall, so they have the same number of protons, same number of electrons. If we lose 2 electrons, it's going to have a 2 plus charge. Okay, and notice how part B is a 2-mark question. So if you say 2 plus charge, it will get you 1 of the marks. What you really need to do is you need to take that 2 and you need to multiply this number by 1.6 times by 10 to the minus 19 coulombs. Okay, and that will give you an answer, and from there you should get an answer which is 3.2 times by 10 to the minus 19 coulombs. Okay, so that is your answer to part B. Part C says, which constituent particle of this ion has a 0 charge per unit mass ratio? So the charge per unit mass ratio is all on about specific charge, so that is the charge divided by the mass. So charge per unit mass ratio, 0, 1 has to be the neutron because the neutron has a 0 charge. Part II says that the largest charge per unit mass ratio. Now you can just remember this, or you can work it out. It's going to be the electron. I would just take that as face value, remember it for future questions, but if not, you can prove it by the relevant calculation. Part D tells us to calculate the percentage of the total mass of this ion that is accounted for by the sum of its electrons, or by the mass of its electrons. So we know that the element has a proton number of 18, and if we are losing 2 electrons, it therefore has 16 electrons. We're going to multiply it by the mass of the electron, which is 9.11 times by 10 to the minus 31. Okay, so that's for the electrons, and we're going to divide this by the total mass of the protons and the neutrons. Okay, because it's the total mass of the ion by the mass of the electrons. So the total mass of the ion for the protons and neutrons is 37. We're going to multiply that by 1.67 times by 10 to the minus 27 kg. Okay, because that is the mass of a proton or a neutron. If you work that all out, and then what you can do is you can also multiply this all by 100. Multiplying it all by 100, you should get an answer. If you plug that all into the calculator, and the answer that will give you is that you should get 2.4 multiplied by 10 to the power of minus 2%. Quite a small percentage for the electrons. Okay, moving on. Question 4. It's saying the neutral atom contains 28 nucleons. Write down the possible number of protons, neutrons, and electrons contained within the atom. So we can just take a guess. If it has 28 nucleons, there's a large number of possibilities for this. I'm just going to say that it has 13 protons and 13 electrons because it's neutral, and therefore if it has 28 nucleons, we'll say that it has 15 neutrons. That's just 28 take 13. Alright, and part B says that a certain isotope of uranium may split into a cesium nucleus or rubidium nucleus, 4 neutrons in the following process. Okay, so that's a decay equation that you should be able to see over there. Explain what is meant by isotopes. So isotopes, they have the same number of protons but a different number of neutrons. How many neutrons are there in the cesium 137 55 nucleus? Okay, so for that question, we're just going to subtract 55 from 137, and that will give you the answer. Part III, calculate the ratio of the charge to mass ratio in coulombs per kilogram for the uranium-236-92 nucleus. Okay, charge per unit mass. So what we're going to do for that calculation is do the charge. So that is going to be 92 multiplied by 1.6 times by 10 to the minus 19. That is the charge on all the protons over there. Divide that all by the total mass, which is 236 multiplied by 10. Multiplied by 1.67 times by 10 to the minus 27 kilograms, and that should give us an answer which is 3.7 times by 10 to the power of 7, and that's coulombs per kilogram. Okay, so that's the answer for that question. Part IV now asks us to determine the value of X for the rubidium nucleus. So to calculate the value of X for the rubidium nucleus, we are just going to use the basic rules of conservation of mass or whatever. that is in the equation. So if you look here in the equation, we can add 236 and 137, and we can subtract 4 lots of 1 from that, so just 4, and then that will give us an answer overall of 95. So it's literally just adding up the masses on this side and subtracting the mass of the nucleuses. So that's 4 times 1, which is 4, giving us a value of x, which is 95. Okay, that's how we do that question. Moving on, we are going to do question 5. Question 5 is asking us that we have a particle, an alpha particle is the same as a nucleus of helium, and they've given us a equation there, and that's representing the decay of the thorium isotope by the emission of an alpha particle. We need to determine the values of x, y, as shown in the diagram. So if we look at this decay in a bit more detail, this is standard alpha decay, so what we can just say is if we just draw it out, we have thorium 229 90, that's going to radon plus alpha we know is 4 and 2, okay, and so it's just going to be 229 subtract 4, which is just going to give us 225, and then 90 subtract 2, which is just 82. Okay, so we can calculate all of that from that. That's how we would to do that question. Right, let's move on. So we'll back up at the top now on question number 6, which is describe an alpha particle and state its properties. Okay, so an alpha particle we know is a helium nucleus, so very basic. That's an alpha particle for 2. It's basically a helium nucleus, mass number of 4 and a charge of 2. Part I says that astatine 218 is an isotope of an element astatine. Okay, so we just said that, which decays into an isotope of bismuth by emitting an alpha particle. Write down the equation to represent the reaction. Okay, so it's just a classic decay equation that we have to do. So we can say that 218 and 85, I think that is. Yep, 85 astatine is going to decay into bismuth and emit an alpha particle of 4,2. Okay, so what we just have to do is just take away from these sections over here, and that should be nice and simple to do that. So what we're going to just do is we're going to say that we have 211 over here, because that's 218, take away the alpha particle. Sorry, 215, my bad. That's meant to be 215 over here. 215 take away 4 is 211, and 85 take away 2 is 83. So that's the decay equation. Again, if you are confused on that, have a look back at the other video. It's just astatine over here. Alpha, you just have to remember, is 4,2, and you're subtracting the 4 from 215, and you're subtracting the 2 from astatine from 85 over there to get these numbers over here, so everything's balanced on either side. Okay, carrying on, part B, it says state what happens when an unstable nucleus decays by emitting a beta minus particle, and then write down the following equation. So when we emit a beta minus particle, that is, if you remember it in terms of the Feynman diagrams. So the Feynman diagram says that we have a neutron over here. Just bring it up a bit. We have a neutron, and that neutron goes into a proton over here. There is an exchange particle, which is the W, because it's beta minus, it's going to be the W minus boson, and we emit a beta particle, and we also emit a anti-neutrino. Okay, so that's the Feynman diagram. W minus boson is the exchange particle. That is just so that it can become more stable. So that's kind of what happens when we emit a beta minus particle. Next question says, write down and complete the following equation showing an isotope of molybdenum decaying into an isotope of technetium. So it's just a classic beta decay equation. So we're going to start with MO over here. We're going to have 42. Okay. This right here is going into technetium 99. We do know about beta. Beta is just 0, -1. 0 up top, and then we have the anti-neutrino, which we don't need to worry about because it's just 0, 0. Okay, cool. So let's try and fill in these gaps. Right, if we've got a -1 here, that's got to be 43. Okay, because 43 minus 1 gives us 42. So it's conserved on both sides, and at the top over here, because that's a 0 over there, that also has to be 99. So we're going to have 99 over here as well, and that makes everything balanced. So that's our beta minus decay equation right over there. Okay, and moving on, what we have is question 7. In a radioactive decay of a nucleus, beta plus a particle is emitted following a gamma photon of wavelength 8.30 times by 10 to the minus 19. State the rest mass in kg of the beta plus particle. Because it's a beta plus particle, it is essentially a positron, and positron is the same as an electron, so we have the rest mass, which is equal to 9.11 times by 10 to the minus 31 kilograms. Something to remember from previous videos. Moving on, we say calculate the energy of the Y photon. So to calculate the energy, we have to go through a bit of a calculation phase. So look at the data that you've been given. You've been given the wavelength of the gamma photon, and we want to calculate the energy of it. So for this is a classic type of question that they use. We know that it's a gamma photon, we know it's part of the EM spectrum, therefore it's going to travel at the speed of light. Therefore, what we have to use is the equation C is equal to F lambda. C is equal to F lambda. C is the speed of light, and lambda is the wavelength, and we can calculate that. From that we can calculate the frequency. So if I rearrange that, we get that the frequency is equal to C over lambda. Okay, and we can say that that is 3 times by 10 to the power of 8, which is the speed of light that the waves travel, divided by the wavelength, which is 8.30 times by 10 to the minus 13 meters. Okay, and that gives us a frequency, and that frequency that we have is 3.61 times by 10 to the power of 20 hertz. So that's our frequency. Now, once we have our frequency, we need to calculate the energy. The question is asking us for the energy. So we're going to take this frequency that we have over here, and we're going to multiply it by Planck's constant, 6.63 times by 10 to the minus 34, in accordance with E equals HF, and that will give us a energy, and that energy that we eventually get, which is our final answer, is 2.4 times by 10 to the minus 13, and remember the unit for that is all in joules. That's how we do that question to determine the energy of the gamma photon. The next part of the question is very, very classic. They ask you to calculate it in mega electron volts. So to calculate it in mega electron volts, we need to remember the equation. J is equal to EV. So we've got it in joules, we just want to divide it by E, which is 1.6 times by 10 to the minus 19 to get it in electron volts. I know it says mega electron volts. Hold your horses. E is equal to 1.5. No, it's not. What am I saying? E is equal to what we just calculated, which is 2.39 times by 10 to the minus 13. Now, I said 2.39 here. Obviously, in the previous question, I rounded it. And then we're going to divide that all by 1.6 times by 10 to the power of minus 19. Now, because we want it in mega electron volts, after that we'd have to divide it again by 10 to the power of 6, or what you could do is you could just get rid of that 9 and put a little 3 there, and then make it divided by 10 times 1.6 times 10 to the minus 13. That's just maths. Right, moving on. State the fundamental interaction or force responsible for beta plus decay. Well, beta plus decay, the exchange particle that we knew in the Feynman diagram that I drew before, is that it is a weak interaction. Don't know what happened to the W there. Weak interaction. Okay. Moving on. State the antiparticle of a positron. Describe what happens when a positron and antiparticle meet. Well, the antiparticle of a positron is a electron, and when they meet, they annihilate, and 2 gamma rays are released. So annihilation. We have our electron, we have our positron, and we have our gamma rays being produced. That's annihilation. Moving on. Calculate the minimum amount of energy released as radiation energy when a particle of rest energy 0.51 mega electron volts meets its corresponding antiparticle. When it meets its corresponding antiparticle, we have 2 photons produced, and therefore if we have 2 photons produced, then we are going to need to double that. So we have 0.51, which is the mega electron volt energy, and we're going to multiply that by 2 to get 1.02 mega electron volts, MeV. From there, we can multiply it by 10 to the minus 19, 1.6 times by 10 to the minus 19. So we get 1.02 multiplied by 1.6 multiplied by 10 to the minus 19, and that gives it to us in electron volts. Then, like I said, we can either divide it by 10 to the power of 6, or we can just make that a little 3 over there to get it in MeV. So that is how we would calculate the minimum amount of energy released as radiation energy when a particle of rest energy 0.51 mega electron volts meets its corresponding antiparticle. That's all done there. Right, moving on. Right. In a particle accelerator, a proton and antiproton traveling at the same speed undergo a head-on collision, and they produce subatomic particles. The total kinetic energy of the 2 particles just before the collision is 3.2 times by 10 to the minus 10 joules. What happens to the proton and the antiproton during the collision? So, if we have a proton and antiproton during the collision, like we just explained in the previous question, they are going to annihilate each other. And when they annihilate, they will produce 2 photons. State why the total energy after the collision is more than 3.2 times by 10 to the minus 10. So that is simply because that the rest masses must be added. If you think about it, when they collide together, we have the energy of the speed at which they're traveling with, so their kinetic energy, and we also have to add on to the rest energy of the particle, which is just the energy stored inside the particle. If you like, it's their potential energy. Moving on, we have question part B of the same question. Part B asks us, in the second experiment, the total kinetic energy of the colliding proton and antiproton is greater than 3.2 times by 10 to the minus 10 joules. State 2 possible differences this can make to the subatomic particles produced. So if we are having more energy going in, then we could potentially get more subatomic particles. The particles could be a lot bigger, or they could have a bigger kinetic energy. All of those reasons make perfect sense, because if you think about it, more energy, okay, put another particle. More energy, just make it bigger. If we have more energy, simply add it to kinetic energy source of the particles in the first place. Okay, right. Moving on, we are now on question number 10, I believe. Okay, so question number 10 says, an electron may interact with a photon in the following way. Name the fundamental force required. So that's just electron plus proton gives you neutron plus neutrino. That is a weak interaction. Moving on. Give an example of an exchange particle other than the W plus or W minus particle. So you could have gone for, remember that the gravitational force does not have an exchange particle, it hasn't been discovered yet. I would always go for the gamma photon for the electromagnetic force. And state what roles exchange particles play in an interaction. So roles for exchange particles, the main ones are the transfer of energy, because any reaction, it's all about transferring energy. It can also be transferring momentum. Marks would have also got you the mark for saying force or charge, but I would always go for energy or momentum. And moving on, it says, the last question, it says, describe what happens in pair production and give me one example of this process. So in pair production, we have a high energy photon. It comes in and it produces 2 opposing particles. We get a positron and an electron, or a proton, antiproton, neutrino, antineutrino, whatever it is, but it's just converted into a particle and it's antiparticle. So those were the end of those 12 questions. They amounted to around 56 marks. See how many you got right from there. And as I said, we're going to continue with this question series for the rest of the chapters. If you have any questions of your own, leave them in the comments down below. Like and subscribe to help us improve the content. Thank you very much for watching.